6.3, Generalized Fourier series and Orthogonality. So for f, g, and w, complex functions, so let them each be complex functions. For square integrable f, g, and w, the inner product of f and g with weight function w over the interval a to b is defined as this, where the bar over g denotes the complex conjugate of g. So there's a lot packed in here. Square integrable essentially means that if you take the square of it, so you take the absolute value of the complex function, then you square it, and you integrate that over the entire domain from negative infinity to positive infinity, that you get something less than infinity. So something that's finite for that integration. This is a real interval, right, from a to b. In x, the variable of integration, it's real. Now, this generalizes pretty easily to a larger space. So you can do functions over R, complex functions over R. You can do complex functions over R2 and R3, etc. And when you take this integral, what you do is instead of integrating from a to b, you integrate over that surface if it's R2 or that volume if it's R3. So this does generalize to higher dimensions, and that actually is useful when you're looking at multidimensional PDEs. But for our purposes, it's probably best to start with this definition. So this inner product of functions can be considered analogous to the inner or dot product of vectors. Okay, so with vectors, we would take the dot product of them, and we would get back a scalar, right? This, you take in two functions, and it's a definite integral, and you get back a scalar, okay? The weighting function w is 1 for a lot of the cases that you'll see. When we take the inner product of sinusoids, typically the weighting function is just 1. For polynomials, though, like the Legendre polynomials and stuff, there's a weighting function that is non-unity. So that in general is in there. It's good to keep it close by. The Fourier series components can be found by a special property of the sine and cosine functions called orthogonality. In general, functions f and g from above are orthogonal over the interval a to b if and only if their inner product with respect to the weight function w is 0. So similar to how a set of orthogonal vectors can be a basis of a vector space, a set of orthogonal functions can be a basis for a function space, which is a vector space of functions from one set to another with certain caveats, like it has to have an inner product defined on it and all that. So this, you can see sort of the analog here, where you take the dot product of two vectors that are orthogonal, and you get 0. Take the dot product of two functions that are orthogonal, or the inner product of two functions that are orthogonal, and you get 0. So inner product is the more general term for this type of operation. The dot product of vector calculus is just a type of inner product. Okay. Great. In addition to some sets of sinusoids, there are several other important sets of functions that are orthogonal. For For instance, sets of Legendre polynomials and Bessel functions are orthogonal. Okay, so sines and cosines can be orthogonal, where if you plug them into 619 here with a certain weighting function, just 1 in the case of sines and cosines typically, you will get 0 for the inner product. That also happens with certain polynomials like the Legendre polynomials and Bessel functions as well. As with sinusoids, the orthogonality of some sets of functions allows us to compute their series components. Okay, so that orthogonality really shines as a property when you say, okay, how would I write this function that I know, like a square wave or any arbitrary function, as a sum of other functions with different components associated with them, different coefficients. So orthogonality is actually really important when we derive how to find those components, those Fourier components when we do Fourier analysis. The derivation of those formulas is essentially that Fourier analysis formula comes from requiring that those functions are orthogonal to each other, sine and cosine. So that actually means that you can do something similar for other sets of orthogonal functions, not just sines and cosines. Let functions f0, f1, etc. be orthogonal with respect to weight function w on interval a to b, and let alpha 0, 1, etc. be real constants. A generalized Fourier series is, this is Kreisig too, I don't know why it didn't show up, given by 621. So we sum the component or the coefficient multiplying the function associated with it. So you get a coefficient and a function, a coefficient and a function. Sum it up. And this represents a function f as a convergent series. Okay. It can be shown that the Fourier components alpha m can be computed from this general formula 622. So we've got the inner product of f, the function that we're trying to come up with a generalized Fourier series for, with that specific orthogonal function fm. So this might be, in the case of sines and cosines, this would be like sine of 2 times, m is equal to 2, so like 2 times the fundamental frequency times time or whatever. So you multiply it by, or you take the inner product of those two together, and then you take the inner product of that specific orthogonal function with itself. That's what you use as sort of normalizing factor here. And this is sometimes called the square of the norm of f. I didn't introduce that terminology here because I don't think it's that helpful, but square of the norm of f is equal to that. So for what it's worth. Great. In keeping with our previous terminology for Fourier series, equation 621 and 622 are called general Fourier synthesis and analysis, respectively. So 621 is the synthesis where you sum up all these components, you get the function, the original function you're trying to write a series description of. And then 622, you are doing the opposite, where you're breaking it down into all the components. For the aforementioned Legendre and Bessel functions, the generalized Fourier series are called the Fourier-Legendre and Fourier-Bessel series. These and the standard Fourier series are of particular interest for the solution of partial differential equations, which is in chapter 7 that we're going to go to next. So that's our next topic now is, now that we know how to do generalized Fourier series, now that we know it's the orthogonality of the sine and cosine that really was important, there are solutions that can be written down for these partial differential equations in terms of not just the good old-fashioned Fourier series, but also in terms of these generalized Fourier series like the Fourier-Legendre and the Fourier-Bessel series. Okay, these are going to come in very handy for us. Yeah.
So when we say the inner product between the two functions, I mean fm is given. How about f for the alpha m here?
Yeah. So.
What is f?
So f is whatever function you're trying to write the generalized Fourier series for. So say you've got some function like we did in the Fourier series example. We had a periodic function like a square wave, and then we said, okay, if you sum up enough sines and cosines at different frequencies and amplitudes together, you can represent this function in the infinite convergent series if you sum them up. So what we did was we said, okay, those an and bn components can be computed from a formula that actually is a specific version of this. 622 is the more general formula. But when we computed our ans and our bns, what we were saying is, oh, okay, these coefficients of these functions are computed by the Fourier series, by the Fourier analysis of 622. And these FMs are going to be, so for the sine and cosine, the FMs were things like sine of some, n times the fundamental angular frequency times t, for instance, for the sine series. This would have been, and so this would have been like our f sub n in this case. And then we wanted to compute for that f sub n what is the coefficient of it. So that's going to be there. We want to know what's the alpha that we need to multiply it by to represent this function. And so for n equals 1, a lot of times that's the fundamental frequency component. A lot of times that's large, right? We saw that fundamental component is usually pretty large in magnitude. And then usually they drop off. But sometimes they don't drop off immediately. Sometimes they fluctuate a little bit before they drop off. It kind of depends.
So in this case, if we know fm here, we want to compute inner product between f and fm. And we relate back to 619. How do we do that? Because we have to know gx.
So f and g, so in this case you're taking g is fm. Yeah. The weighting function, so in the case of sines and cosines, we take the weighting function to just be 1. For the Legendre polynomials, for instance, the weighting function that gives you orthogonality is something else. And so I think it's an exponential. So their orthogonality has to be with respect to some weighting function. In certain cases, we'll take w to be 1. In other cases, we'll take w to be some other function. And as long as these functions are orthogonal with respect to some weighting function that we know, we can essentially derive an equation like 622 will apply, as long as there's some weighting function that gives us that orthogonality.
our function here is also related to time. For example, f, we want to approximate f as a step function here. So we have to write f in terms of time.
Yeah, I mean, I put t in there because I'm just so used to using t. But let's just say this was x. So this was fn of x. So this would be for the sinusoidal, good old-fashioned Fourier series. This would be one of the fn's for a Fourier sine series, at least.
So f here is the step function there. So
yeah. So f is this square wave function. So we would need, when we take this inner product, we would be taking integrals over that interval, which we would take to be one period, and we would take that one period of f,
and then divide into half and half.
and then if in this case of the square wave, we would divide it into different intervals where we can evaluate it and go forward. So yeah, so this is where that that formula comes from for the Fourier analysis. Well, it's a generalized version of that process, essentially.
So in this case, no matter how noisy the function that we want to approximate, so we just take more interval in that case.
Yeah. There are caveats to like the types of functions that you can approximate, but essentially, most any function that you're going to want to approximate in a partial differential equation solution is something you can write a Fourier series for, or a generalized Fourier series for. Like I think that like a fractal or something like that would not. I don't think that they have valid Fourier series for them. But there are caveats. But for most of the types of functions that we would want to approximate, like a square wave, or anything that you can describe with a polynomial, or anything you can describe with exponentials, we would be fine in writing a Fourier series for it. And it only perfectly describes the function if it's continuous. But if it's discontinuous like this, remember in the limit, when you take all the terms together, the one thing that is different is that you get a point that is the average of the two endpoints of the discontinuity. So it's usually, for our purposes, that's totally fine. That doesn't bother us at all. Yeah. So we'll be using this to solve partial differential equations. We'll be using the fact that you can write these series to approximate functions. And in particular, we'll be interested to describe our the spatial variations of our functions in, say, their initial condition, which can be extended out arbitrarily to be it's like an odd function or whatever. And then we can write a Fourier series, generalized Fourier series for it. And then with those nice properties of the Fourier series, we can get out solutions. There'll be series solutions, so there'll be solutions that are also infinite sums. But a series solution is better than no solution. And sometimes you can identify, and you guys did this in calculus too, calculus also. You identified which transcendental functions are associated with different series, right? Different infinite series. So you could get an answer that's an infinite series and say, oh, that's just the sine of something plus the cosine of something, or whatever. Like you could identify that this is a transcendental function that you can recognize. although that's not necessarily required. I mean, the series solution is valid. It's just you may or may not recognize that it's a function you don't have to write as a series. And actually, Kreisig does that in the modeling of a wave equation in a string. So that's like the first example that Kreisig does. And the series solution turns out to have an easily recognizable relationship to the original series. And so you can write it as like a space shifted and time shifted version of the original series, which is pretty cool. But that doesn't always happen. You don't always end up with that. So I don't really emphasize that part, but it's pretty cool how that works. I like the way that he does it in that lecture. It's kind of fun. That section, 12 point something, 12.1 or 2 or 3. Early chapter 12. Okay, so any questions on the inner product of functions, the orthogonality of functions that comes from the inner product being 0, the generalized Fourier series, or anything related to that? Okay. All right, we're in for some good fun now. Now we've set the stage. Okay? All right.